in this talk, I'm going to assume that some people know about feature engineering, other people don't. And so I'm going to provide some basic framework for like understanding where feature engineering fits in the entire end-to-end machine learning process. And to sort of explain and give you some ideas about how you can adapt this to your own work, I'm going to go through an example using a real data set provided by the Kaggle website that is going to basically give us an opportunity to show how we can iterate through a few different types of experiments and sort of the process that I took to go from a relatively meager score to a pretty high score within just a short period of time. So without further ado, let me quickly introduce myself beyond what was just said. So I am working for a company called Data, whose product I'll show a tiny bit of today, which is a company that focuses on feature discovery. And how I got here was, first I was working in insurance, and then I decided to pursue my PhD in statistics from the University of California, Los Angeles. And while doing that, I studied algorithms and time series forecasting, and essentially my focus was on trying to predict earthquakes, which, you know, obviously if we knew how to do that, the world would be kind of a better place. But I learned a lot in doing that. And so my industry experience, while I was doing the doctorate, I continued to work in insurance and financial services. And then I switched to a role in manufacturing and R&D. And in this role, I did focus primarily on defect detection and computer vision and deep learning frameworks. And that was a really great experience before I joined Data. Now, I really like Data because it kind of is a synthesis of all of my interests, right? We have machine learning as a very diverse and complex field. And then what people don't really understand is that feature engineering is a fundamental component to it. And so I have interests in time series for sure, as I study that in my doctorate, in addition to deep learning and computer vision. And then now working at Data, I really focus on machine learning and feature engineering. And beyond that, outside of this, kind of professional setting, I'm an avid triathlete, and I'm also a triathlon and endurance coach. So now you know a little bit about who I am. I'm going to jump into the actual content. So in this talk, I'm going to focus on a few things here. The first is, to define what is feature engineering, and everyone has a sort of different idea of what feature engineering is. You might think, oh, that's feature extraction, right? Oh, that's basically transformations, right? Like log transformations or something. And so here I'm going to sort of lay the groundwork for what are different types of feature engineering and what does it actually mean. Then I'm going to present this data set, which may be similar to some data set that you guys are working on in your current workflow, or maybe something that you've seen, which is going to be a time series data set. So I'll present the time series data set and what it's trying to accomplish by using this machine learning and feature engineering. I'm going to outline a few different experimental approaches, and in this kind of approach, I'm going to explain like how I would approach a similar problem. And I'm not just saying this from like an academic or conceptual theoretical framework here. Like we as a company at Data, we get a lot of new customers, right? And they have very complex projects. So this is the same approach. If I got a call today to do a new project, I would apply this the same exact approach. And so I'm going to basically tell you what that approach is, and then I'm going to dive into some of the specifics of that approach, and hopefully you'll get an idea of, okay, I have this data set, someone asked me to analyze it. What do I do? How do I show small steps of progress with it? And then I'll summarize, basically summarizing everything that I showed and then explaining how I progressed in this iterative approach. And prior to this presentation, I wanted to give an opportunity, and this slides will be shared out, or you can take a screenshot of this. Data has done a few webinars in concert with ODSC, as well as some other content that we've put out, either in terms of blogs or webinars that we've run outside of like a kind of larger setting like this. And I wanted to just highlight two of them that you can take a look at. I think the first one is done. It's basically more detail in terms of like, okay, if I have to do a time series problem, what are the kind of things that I need to think about? What are some of the common issues with the data as it comes in? How do I actually set up a forecast? Like what's the difference between a direct forecast, recursive forecast? Should I use the REMA, profit, these kind of things? And we cover that in this time series analysis and forecasting webinar. And then we also have one on feature engineering for predictive maintenance. So if you don't know what that is, it's kind of like, okay, we have this HVAC system, and it needs to be maintained every month or every 6 months, and if we don't, it could break, right? And what you can do is kind of model all of the pieces that go into that to try to predict, hey, we need to service this thing a few months before it breaks. And these are just two types of problems that feature engineering plays a fundamental role in helping to solve, and that we see very often. So I wanted to bring out the opportunity for you to check out these webinars if you are interested in learning more after today. Okay, so let me slow down with this slide. It's a lot to take in, and explain kind of level set where we are and then where we're going to go with this. So first, the step is to define what is feature engineering, right? So a feature is basically some characteristic of your data set that you can use to help enhance the accuracy or reduce noise when you're building a model, right, for prediction or classification. So you could use features in the context of many things, right? And today we're going to talk about them in the context of forecasting demand for certain products, but you could also use them to decide if something is going to fail, if a COVID test is going to be positive or negative, right? There's many things that a feature can be used for, but the fundamental part of it is that it takes some aspect of your data and transforms it into something that can be better used to explain some phenomenon. And typically this can be done just by extracting information from a single column. And I'm going to give some examples of that. I guess one for now would be just extracting something like the hour of a day from a timestamp. That would be a very simple feature, or the day of a month. So basically you have a column and you're trying to extract out some information that's already in there, and then adding it to your model or adding it to your set of input data, which would allow you then to somehow better describe whatever you're trying to predict. Now, it can be a lot more complicated than that, and we're going to go through that. But feature engineering kind of takes it one step further, because it's not just about creating or extracting these features, like taking the day out. It's also about selecting the features, right? So there's a multi-stage process in machine learning and feature in model building, where you can just create all the features you want, right? I can multiply someone's age times their weight times their height, right? And then I can square it, right? And these would be kind of all you'd call features, right? A times B and so forth. But there's a limit to how many of those things that you can add before your model would overfit, right? Or you're basically just adding noise without any additional predictive power. So there's some element of feature selection that needs to also take place. And how do you do that, right? And so we would think that feature engineering here is kind of in the middle of our end-to-end pipeline, right? So I'll quickly walk through this pipeline. But as a data scientist, I'm not sure everyone's background here, but I have a story that I always tell at one of my jobs, where we actually spent 3 months creating one feature, right? It was like some crazy feature. We're looking at the inflection point after this one thing could happen or it couldn't happen, and we're calculating the slope and all these things. And that's a really complex feature that took engineers working collaboratively across the globe to figure it out, but it was highly predictive. So this feature engineering thing can be as easy as, hey, I'm going to take the hour out of this column, or it can be as complex as, I'm going to spend 3 months with R&D to try to figure out the exact thing that's going to describe this phenomenon, right? And so this middle step here can be quite variable in terms of how long it takes. But from an end-to-end standpoint, typically a problem comes in, right? And there's this process that needs to take place, from defining the requirements all the way to delivering a solution, right? So the first thing is typically, like, you don't ever just get a data set and be like, hey, let's just analyze this data, do some EDA for the fun of it. Usually there's some sort of business use case, like, hey, we want to prevent customer churn. We want to be able to predict the grocery store sales of certain products, so we know that they need to be stocked, right? We need to allocate those ahead of time so they're there and there's not a rush on those products, right? So there's some use case that needs to be defined, right? Then this next step can be extremely tedious as well, right? Is like, we have this thing we want to solve, but where is the data, right? And so the data can be in disparate sources in different databases. It can be on some NAS somewhere, someone's CSV file, something like that. And so this data collection is also quite challenging, right? And even once you collect the data, you could have these data cleaning challenges. Like, one common challenge that we deal with all the time is, okay, this data is irregularly spaced in terms of time, right? For one of these data sets, it's recorded every minute. For this other data set, it might be every minute, every 5 minutes. It could vary depending on when somebody enters it, right? So there's some assumptions and things that you have to do to prepare the data, right? And feature engineering can actually help overcome a lot of those challenges by, doing rolling averages, these lag features, and so forth, right? And so, this data collection and data prep is very time consuming perhaps. And then once you have all your data, right, then you start having to go through this process of feature ideation or constructing feature hypotheses. So this can be, very simple as saying, hey, let's just take the value from the sales number from the same exact day last year, right? There can be many different ideas for features, right? And the issue becomes, how do you, ideate all of these ideas, right? You need to have some people sitting around being like, okay, this is a good idea, that's a good idea. Or you can write some code, which I'll show how to do, like, okay, let's just take a bunch of these ideas, make a very simple thing. Let's take the lag of the last week, 2 weeks, 3 weeks, and so forth. And then we can create a model just from that, and then we'll see if that works. So basically, the feature engineering can be very simple to very complex, and we're gonna go through that. The next two phases are, very important. And everyone thinks, oh, machine learning, data science, this is where I wanna spend all my time. But anyone who's actually executed this end-to-end project, right, knows that fitting a model or using something like AutoML nowadays is quite trivial, right? I mean, it's like there's so many different libraries and platforms. You can just say, okay, import, PyCare, import sklearn, right? Go. And so the key is not that you can fit 10 different models in a leaderboard, in a matter of minutes. It's actually what is the input to that model that's going to kind of determine how accurate it is, right? And then once you get to the model that you decide and you do through model validation, which is not the topic of this webinar, then you have to deploy it, right? And there's many ways to do that, like MLOps kind of platforms and so forth. And so for the talk today, I'm gonna focus primarily just on this thing highlighted here in light blue. We're gonna talk about the data itself for this project and how to kind of look at the data doing EDA, and then how to discover and iterate and create features that can describe and overcome some of the issues and limitations of the data that's available. Okay, so now that I've said all that, and hopefully you have an idea now of like what feature engineering is, maybe a little bit more than you did. The question becomes, why is it important to do feature engineering? Like, why does this matter? Why can't I just take my, my flat table, right, that has my sales in the one column and everything else in the other columns, and just say, okay, go, right? The reason that is, you can obviously do that, and that's something that we're going to try here as the first iteration. It doesn't provide the best performance, right? There's other information that you can be using to add into this, table, right? You have the thing you're trying to model, regress, or classify, right? And what you want to do is add in the most meaningful information and patterns to that data, right? And how do you do that, right? Feature engineering is one of the key ways that you do that, besides getting the right data, as I talked about. And so what iterative feature engineering does is it allows you to create many different ideas and then pick the ones that are most impactful. We have like a saying in statistics called like the curse of dimensionality, which maybe some of you have heard of, and I briefly talked on it a second ago. But it's essentially that you cannot just keep adding features to infinity, right? Because there's a lot of problems. Like there's computational cost, there's overfitting costs, there's just basically, you want the data to be explaining the phenomenon in the least possible amount of information. We'd call that a parsimonious model, right? You want something that isn't really likely to overfit. You want something that's simple and easy to understand. And so feature engineering allows us to take the most meaningful things that we find and then build that model. The other thing is when you are doing this kind of project, you're going to look at the data, right? You don't just say, okay, this is a black box, press go, right? What you want to be able to do is say, okay, there's some new data that's coming in, right? We have a new product line, right? We have a new magazine or something like that. We have a new something that comes in, and we need to be able to quickly develop a set of features that better explains the output based on this new information that we know, right? And so this feature engineering allows us to quickly update our models by incorporating that new variable or information. And that's where the last thing here is that domain expertise comes in, right? As data scientists, you can just code all you want. You can look at correlation plots. You can do exploratory data analysis, Plotly, anything that you want, dashboards. But at the end of the day, these domain experts, right? People in your business that know how things work, right? there's somebody out there that, they can just like think about it for 10 minutes and just be like, okay, that store is going to need 20 units of that product, and then you could try to build some model, right? And it's never going to come close to this person who's been there for 25 years, right? Just to be able to tell you that. So being able to, leverage domain expertise, but still incorporating that information into the feature engineering aspect is going to be really powerful for you to be able to do that. So now we kind of know what feature engineering is and why we want to do feature engineering. I'm going to just go through my approach here, and then we're going to go in detail a little bit more. I'm going to explain some of the things that I did and why I did them, and hopefully give you some ideas about how you could use these in your own work. So how do you iterate on feature engineering, right? So the first kind of thing that to do is to look at your data, and I'll explain the data for this use case that I want to go through here in a second. But the first thing to do is to actually do exploratory data analysis, which is not the focus of this talk, but essentially there's many tools to do that, and you probably have your own method to do that, right? There's plotting, there's summary statistics, there's fitting some very basic models, which we're going to go through. And then the idea is to discuss this with people, or look for insights elsewhere, like online, or in this case, I'll talk about like I was using Kaggle, right? There's a lot of discussion about, hey, this feature works, this feature doesn't work, right? And so this idea of feature hypothesis, right? Like these are ideas about features that could work based on your prior experience as a practitioner or using information from domain experts, right? And so this is kind of the initial phase, is to think, okay, if I'm trying to predict sales, a month from now, of the product, what are some of the things that might be useful for doing that, right? Should I use the sales from today? Should I use the sales only on the weekend? What if the day I'm trying to predict is on a holiday? How do I do that, right? Should I use only holidays? And so forth, right? And these are features that you have to come up with, and these are what we call feature hypotheses. Then the second kind of phase is to actually construct those features and fit like a baseline machine learning model, right? You can fit a baseline machine learning model just on your raw data, and maybe that would be part of the data exploration, right? To say, okay, if I just use the data as is without any additional feature extraction, transformations, what kind of accuracy or root mean squared error and so forth am I going to get, right? But you might want to just do some very basic feature engineering, like, okay, I have a date timestamp here. Most machine learning models couldn't natively handle a timestamp, right? What you need to do is extract the day, the hour, the month, and so forth. So I can just kind of show you I'll show you how to do that. And that would be some very basic feature engineering that you could use, right? The next thing is to do some like automated and manual feature extraction. Now, there's a whole slew of libraries out there that can help with this. There's .data, of course, which I'm going to give you a brief glimpse of what that could look like if you wanted to try something like .data. There's other open source libraries, like TS-Fresh, that do time series feature engineering. And so there's some automated ways that you can do feature engineering, and you can Google those yourself, or we can, add some to the list here at the end, that we can send out with this. Then there's also this, manual feature engineering, which, I kind of like wrote this presentation a bit ago, and then I was like, hey, is there really much difference between auto and manual feature engineering right now? Because I can just go ask, ChatGPT, Copilot, what have you, say, hey, can you create this SQL for me to create this feature, right? And it isn't automated in the sense it's not going to do it for you completely, like it's going to come up with the idea. That's what like something like .data does. It will come up with the idea for you. But these automated things like ChatGPT can help you implement things much quicker. And so I kind of would really recommend that, actually, say, okay, I have this idea of a feature, I have my data set, just tell it, I want it to do this, and then it can help you do that, right? And so there's a lot to be said for this utilization of automated and manual techniques, but we're going to go through that. And then the last thing is, with any sort of model development, machine learning, and feature engineering kind of pipeline, is that it's an iterative process, right? How do you iterate on feature engineering, right? The machine learning process isn't just like a linear process that you go through where it's like, okay, I do this and then I'm done, right? What any good model development thing should go through is an error identification, or what we'd call model evaluation or model validation, right? And this is where you look at the large prediction errors, the small prediction errors. You can see where your model is overfitting or underfitting, and so forth, right? And this is where feature re-engineering comes into play. And I'm going to give an example of this in the context of this use case, but it's essentially saying like, I will look at all the errors predicted by my model by a certain segment. In this case, it's going to be the product family. And I'm going to say, hey, this one product family for my test set, right? Or my, if I'm doing cross-validation or something like that, is extremely high, right? Why is it so high? Like, what is up with that? And so then I would look at the data, and I'll go through this, but I'm going to say, can I create a feature that reduces this error specifically, right? And that's what we call like feature reengineering, is like you would have some set of features and then you try to add on to it to mitigate certain things that came up in your data set. All right, cool. So how I want to illustrate these this iterative approach is by sharing with you a data set and a project that you can go on to Kaggle website, and when we send this out, you'll be able to see that here. You can click on it, and this data set is available for you to download, right? And what I like about these kind of projects is, we all have jobs, right? We all have things that we're doing, and there's people out there. I think this one has been up for a few years, right? And so there's hundreds, if not thousands, of people that have, I think maybe it's at 613 teams, right? But they submit multiple things, right? There are many solutions to this and a lot of discussion, and actually just looking at how other people solve this problem can give you a lot of ideas for your own features, right? How do I ideate on my own features? And by looking at stuff like this, very useful. And so the goal of this this data set and this challenge, right, is basically to take a significant portion of training data. In this case, it looks to be like over 4 or 5 years, right, where we have this historical sales, and there's 54 different stores and 33 different products, right? And in this entire data set, it isn't just one table that's already ready for ML, right, to press go. You have data tables that have different resolutions, right? For example, we have this holiday table that's very simple, just has date, and it has the day, whether or not there's a holiday. Maybe I think it says what holiday it is, and there's some other information like whether or not that holiday was moved. Like if we say July 4th was on a Thursday, maybe it would be celebrated, we get a day off on Friday, right? And there's some information like that. There's historical oil prices, there's information like metadata about the stores, like where they're located and so forth. And then there's this transaction data, which is quite interesting because there's many single records, many different records for every store, right? And so the problem is this training table is maybe a certain amount of rows, but these other tables, right? This one is fewer rows than the training table, and this one is more rows than the training table. So how do you actually extract information from this transaction table and add it on, right? And so we'll go through that. And so even though we have like a 4.5 year period, right, we want to only predict for 2 weeks, right? And so the question then becomes, is there anything special that's happening in these 2 weeks? And that kind of goes back to that feature re-engineering thing, which I'll talk about. And these competitions, if you've never looked at one or done one, and every actually business case has a different sort of metric, right? Sometimes this one is root mean squared log error because there's different orders of magnitudes, like TVs cost a lot more than milk, right? And so you want to be able to somehow scale the error relative to the thing, right? And so you don't always want the errors to count equally. So the logarithmic transformation of the error actually helps with that. And this could be one thing that you could think about if they're asking for root mean squared log error. Maybe I should transform the thing I'm trying to predict as well. And these are kind of things that you need to think about. So I talked about the data, but I just want to give you a little snapshot about actually showing you the complexity of the data, right? So here on the right is like a schema of what the data basically looks like, right? We have our training data, our training data, which has the target column, which is the thing that we're trying to predict, which is the store sales, which we call here the target column. And in that table, we only have a few additional columns, right? We have the date, we have the product family, and then we have the store number as well as like a row ID. Now we have these other tables, right? The first is the store table, which has that metadata, and we can see here it's only connected through store number. There's this table here. This other table, the transaction, has both the store and the date, so that's how we can connect those two together. Holiday, just the date, and then we have actually what we want to do to create some sort of a lag or recursive features like we would see in ARIMA. What we can do is we can add this table. Basically, we just want to say, let's use this table as a feature source, right? The historical target information. There's many ways to set this up. And the last table here is the this oil price table. And just to look at what this training table actually looks like here, we have different stores. These are when I say product family, it's just like going to like a Costco or Walmart or something, right? There's different sections of the store. right? And you can kind of maybe think, okay, well, maybe books and automotive are going to have different sales patterns, right? Or and so forth, right? And you can kind of see the complexity of this. We might need to have different types of features for different product families. Okay, so what are some of the challenges of this data set, which kind of, in my experience, represents some, real world challenges, right? The first is this, heterogeneity, right? And that's what I'm showing here, is that not all the product families have the same pattern, right? You'd like to think, okay, sales increases and decreases all at the same time. But in reality, that's totally not the case, right? We have one example here where it looks like for this grocery store chain, even though there's 54 stores, that they might not have started selling books until, the last year. So for this one product, would it make sense for me to generate features that go back until 2013? If I say, hey, let's take the average sales every single day, all the way back to 2013, that's obviously going to lead to a really bad model, right? Because it's all zero or missing, right? You have other ones which are a lot more stable, but you can see here that it's also like non-stationary, meaning that there's a slow upward trend, right? For this one here. So the sales are slowly increasing. And you have other ones that are significantly more cyclical, right? Where it's like, okay, there's periods for some reason that maybe around holidays and so forth that the amount of sales go up, right? So when you do this sort of project, you need to look at all the data and say, okay, what can be modeled together, right? Homogeneously, or what's heterogeneous, right? Which ones need to be done separately? And then in addition to that, there's also issues where there's certain products in this case that will be like complementary products, right? That kind of crowd each other out, right? It's like when one goes up, the other goes down. And so there's interdependencies, interactions between them. And so doing some sort of like, EDA would help reveal these things. The other very common issue then is also this issue of missing data, right? Like how do you deal with missing data? Like do you do missing data imputation? Do you trim your data, which I'll talk about, to reduce the input data? And then once you kind of figure all of those things out, you have to think to yourself, okay, for this type of data, what is the best machine learning model that I can use, right? Is it as simple as me just saying, hey, fit an ARIMA to each of these product categories for each of these stores, which would be like, 1,000 models or something? Or is it better if I try to leverage information across, from different products in the same store or different products across stores and so forth, right? And so you have to kind of think, okay, what's the best kind of model that can handle this sort of complexity of data? So to solve this problem today, I'm going to go through 5 different ways that I iterated, okay? The first is to construct some baseline machine learning, right? And for this whole project from step 1 to 5, I'm actually going to just use one machine learning model, the same framework for all of them, and it's going to be the LightGBM framework. I chose LightGBM because it's really flexible. It works for both regression and classification. It's also really fast. Okay, so when I'm doing like an iterative approach, right, I don't want to do like a really complex model that takes a long time. I would probably do that at the end, right? And I'll talk a little bit about, hyperparameter tuning in the last iteration here. But essentially, I like GBM because it's really fast, and in my experience, it's quite good for this sort of time series use case. So I'm going to fit a very basic light GBM with some very basic initial feature engineering, and I'm going to provide specific examples of what those features are. Then I'm going to briefly show what .data could do as like a very basic, similar minimal configuration, right? Where I would say, okay, import the data into .data, and is it any better? Then I'm going to basically do, what I would do as a data scientist trying to get this thing to work, to try to deliver the results, right? So that's where I'm going to talk about how I kind of partition the data, right? I did something called data trimming, which essentially I reduced the data to be more representative of the more recent future, right? If I'm trying to predict 2 weeks from now, it doesn't necessarily make sense for me to use COVID era data, even though it's available for me as a data scientist, right? The world has changed, right? Pre-COVID, post-COVID. So data trimming in this case proved to be quite valuable for improving performance, right? The next is to basically combine the approaches of 1, 2, and 3. So using some sort of automatic tool like .data or others that are available, as well as some manual feature engineering, and combining them all into one flat table essentially to say, okay, what's the lift when I add step 1 to step 2 to step 3, right? And so that's kind of where the power is because you can do this automatic feature engineering you can add in your own features, and then you can say, hey, is there any lift? Like, which are the best features, right? And then the last, and perhaps more important, and this is kind of an iterative process where you would probably go 1, 2, 3, 4, 5, and then, okay, review. 1, 2, 3, 4, 5, and then review, right? You would do this a few times. It's not just one and done. And that's really what I kind of drive home here, is that you need to continually try to improve your model, right? And how I did this was I did a very specific type of model evaluation where I looked at the type of error for each segment or each product family here. Then I decided that I would combine multiple models together and create some segment specific features for this, like feature and re-engineering, essentially looking at some of the problem product categories and then developing some specific features for those. Okay, so the very first experiment, as I said, was to basically try to take those different tables and do a very basic machine learning model. And for any sort of project, I work with customers, like this is the first step, right? You always want to get some sort of baseline performance to say, okay, this is my data. If I just do some most naive thing possible, and I'll talk about what that kind of means, what do I get, right? Like how good is it, right? And so here, what I did was I wanted to generate around 30 features manually, okay, using some very basic techniques. So the first thing I did, which, you might cringe at this or something, and this is really something I wouldn't recommend, but essentially is I took those tables, right? We have our target table, let's just say for simplicity, it's 10,000 rows. And then I just did a left join, right, on the target table for all the additional tables. So that included this, these tables had less rows, right? There was not multiple rows, right? So that worked fine. But this transaction table, I think was, many transactions for every single store, date, and product family. And so what this join did was essentially only take one row, right? It was essentially saying, okay, take the first row, take the last row. It's doing some sort of, taking only a small bit of information. And how you can overcome that is by doing some sort of aggregation, which we're going to talk about here in a second. But by doing this, I created one table. And then once I had that table, I wanted to a little more feature extraction. And as I said, some of the more basic features that you can do is to extract some of the date information, right? So some of the common things that you would want to do is extract the day of the week, the day of the year, the day of the month, the quarter, and the year, right? So here I just added, I think it's like 7 columns, basically just saying, okay, is in light GBM, can it tell the difference between 2016, 2015, and so forth, right? And so I created these features, or this table. And then what I wanted to do is, beyond adding in all the information from all the tables, the raw columns, as well as some of these basic time series features, is I used a simple loop basically to say, okay, what if I just take the average sales lagged by 16 days, 30 days, and 45 days. 16 days I did because the actual forecast period is 16 days ahead. So we need to be able to predict 16 days ahead at minimum. And so what I did here was I basically said, okay, I'm gonna just take the rolling average, okay, of that time period, right? And there's other ways that you could extend this, like exponential weighted moving averages. You could take the standard deviation, and I'll go through some of those types of features that data generates. But by doing this, I think I came up with around 30 total features. And when I did this, it actually had a pretty decent, I mean, it's not the best performance, but it's one of the, isn't the worst, right? And I got an RMSLE of like 0.53. And so I think by the end, I got an RMSLE of around 10 or 15% better than that. And so I'm gonna walk you through how I did that. So the point of this experiment is, okay, I naively joined everything together. I created some basic features, and I wanna use this now to say, okay, can I do anything to improve this, right? And how Kaggle works is you can't really overfit the test data, because what you need to do is submit it, right, to the leaderboard every single time. So there's no way to say, okay, hey, is this thing over or under predicting, right? You have to do that in terms of using cross-validation or using like a train test split, right? And so basically this allows us, the 0.53 is essentially, okay, this is our first attempt. The next thing is to use like some sort of automated feature engineering, right? And like I said, it's not just .data. There's many things that do this. But I wanted to just give you a glimpse of what .data is, and I could open it after if there's time as well. I have it open here. But essentially what I wanted to do is take that schema and feed it in. And what .data does, it will generate more complex features automatically than what it was just shown, those simple time features like day and week and lag and so forth, right? And so just to quickly look at only, I think, 10 or 15 features here of the thousands that we could explore, it found some like, okay, what's the sum of the sales for each store and product family in the last 7 days, or the standard deviation. It has some things like, okay, there's something called temporal change. Essentially what that is it's looking at a trend within a certain time period. So in this case, it's saying in the last 7 days, is the trend of sales increasing or is it decreasing? And is that day, in this case, is on a weekend or not, right? So it's essentially looking to aggregate your data in such a way that's to say, okay, in the last period of time, is it going up or is it going down? Not just what is the value itself, like the average or something like that. And there's some other interesting features here, like target encoding features. I don't know if you know what that is, but essentially it's like for each group in a category, in this case it says, I think there's something called cluster in stores. It must be like regions or something like that, where it's like these are certain stores in a cluster. It would say, hey, take the average sales for that cluster and use it as a feature. It's sort of like one-hot encoding, but you're essentially taking the average sales instead, or the average of the target value, and feeding that in as an input to your model, right? We also do more complex features that you could try, and this TS Fresh does stuff like this, which is like a wavelet transformation or see-through transformation, which essentially tries to look at some of the really zoomed in kind of features of the sales. Like, okay, is it really spiky and wavy and so forth like that? And so to configure this in .data is pretty trivial actually, and these are not actually the more complex features that we can generate. But when I do this, I actually selected, I think before I fit to light GBM, 50 features here. And when I did this without those other features, it got a performance of like 0.49 RMSE, which was a good, improvement from the very basic feature engineering that I would expect using something like .data. So the next thing is essentially like I wanted to combine those first two things, but also to actually look more closely at the data and say, okay, hey, when I did my EDA, when I showed you on those first few slides, I noticed there's some of these, stores, like this store here, it looks like there's some missing data for this store for some reason, like it closed or something like that, under construction for all I know, right? And then even still, for some, across all stores, there could be some issues like this where there's no sales for certain regions, right? So if you think, okay, let's just say that I wanted to make a feature that tries to predict August 2017, right? Which is like right here. Well, if I look at here, it's possible that there's 0 in August, right? So using like, okay, lagging the past 1 year, 2 year, 3 year, 4 year, 5 year, taking the average, there's some issue with that, right? It's not necessarily gonna work, right? And so what I did was I say, okay, first thing I can do is say, okay, by default, something like .data actually searches for features out a year or beyond. And I don't wanna do that because I think to predict something only 2 weeks long, we don't really need to be considering 5 years of data, right? We actually only want recent data. And so what we can do is say, okay, whenever we're trying to predict, let's say we're trying to predict 2016 January, let's only look at the past 90 days of data, right? And for your problem, it might be the past 30 days, the past 15 days, or whatever, right? It could be some small set of days, or it could be extremely large. You could be looking for year-over-year seasonality, right? In addition to that, I decided that I do not want to include any of this really, really old data, right? So essentially, even though I have all this training data available in this problem, which could be theoretically predictive, I wanted to just say, hey, let's just use the most recent data because I think that's going to be better, right? So I just trimmed the data. I literally cut the data off, I think at like 2017, and say, okay, throw out everything and let's just see what kind of performance that we got before that. And this is actually a quite common approach. And this is, like I said, because of COVID, especially nowadays, or just because, things change, the market changes, behavior of customers change, and so forth, right? And so what I did then is I combined these automated features from .data with those manual features like the day of the week and so forth that I had before. And by doing so, I improved the score slightly to 0.459. Okay, and so by doing this, I basically was able to slightly improve it. And I think most of that, to be honest, came from just removing all this bad data that was beforehand. So that would be one thing that I really would recommend is when you're doing some sort of feature engineering is to say, hey, the features that I create don't need to look back as far, right? Maybe they only need to look back a small amount of time, which is relative to the forecast period. and not use all available data at my disposal in this case. The next thing was essentially to try to extend this even further by using additional tools within something like .data, right? You could do this manually as well by, like I said, you could use something like TS Fresh, or you could use something like ChatGPT to help you, do this. But one of the things that is really convenient about something like .data is there's like a way for you to quickly combine your knowledge with the features that it automatically creates. And so one thing that I wanted to show, just as an idea more than anything, and you don't need to use something like .data, but it's like you have certain types of features, and maybe in your mind you think, okay, hey, whenever I'm doing a time series forecast, I'm only looking at past data to predict future results, right? And by default, something like .data will only do that too. It's configured to prevent leakage, right? Which, if you don't know what that means, is essentially saying, hey, when you're looking at a time series forecasting machine learning problem, you always have all the available data, right? But you actually don't know at the time of prediction what the data is that's going to be available, right? Like if I'm trying to predict 2 weeks from now, what information do I have exactly right now? It could be different based on all those tables. Maybe that transaction table, there's a 2-day lag that comes in. But one thing that we know is that we already know what's going to be happening in 2 weeks is that there's going to be a holiday or there's not. And so one thing that I quickly did was to say, hey, let's just count how many holidays there are. Instead of just looking in the past 7 days, I actually want to look at the number of holidays that are in the past 7 days and also 7 days ahead, right? And so that was just something that I was able to just like, what I did in .data was I just copied the feature. And in your own code with Python, that's quite trivial to implement as well. And we have this idea of what's called a feature space. And essentially that's kind of all the possible combinations of things that you could try. And you might not have any idea what's in your feature space. And that's where something like an automated tool can actually help you, because it can say, hey, given all of your input data, how are all the ways I can slice and dice this? And then from that, you can be like, okay, these are good ways to slice and dice it, and these are bad ways to slice and dice it. So here, what I did is I wanted to extend some of those other things that I showed. Like I wanted to look maybe at the past 7 days and add some more transformations. So instead of looking at like the sum of sales in the last few days, like I showed on that screenshot, I also wanted to look at the max of sales, the min of sales, and then I wanted to do some more complex time series transformations like the wavelet transformation or the C3 transformation. And if you just Google these transformations, you can look them up, and I would say they're kind of fun to play around with because you're like, whoa, this is a really fancy feature and it can impress somebody that I'm coming up with this myself, right? And so what I did is I added, basically extending the feature space that we had, the feature set, from 50 to 100 features. And then using, all these techniques together, I further reduced the score down from 0.45 to 0.44. And so the goal of this slide is essentially saying like, okay, there's some domain specific information that we can incorporate. And in this case, I think I got this from looking at the discussion board. Basically someone said, hey, you should see if there's a holiday in the future and that could work to improve the performance, right? And so what I did was then I incorporated that domain specific information into my semi-automated and semi-manual feature engineering set that I already created. And I did that for a few different things. And that allowed me to further extend the performance. Cool. So the last thing is essentially this feature reengineering and error analysis. Okay. And so what I wanted to do was here, basically I'm showing this training period, which I've actually cut off, so we can kind of ignore everything to the left of here because the data has different lags. Like there's some things that are 90 days, there's missing data and so forth. But I was really focusing on here is I'm showing the error for each product family, right? Based on the model that I already trained and the set of features that I already created, right? So essentially what I had was, this is the training error, but I have the difference between the observed value, which was the actual value, and the predicted value, right? And I look at it and say, okay, for each of these products, where is my model performing quite well and where is it performing not so well, right? And so what you want when looking at a graph like this is for each product family, you want to say, hey, I want the error to be basically 0 everywhere, right? I want the error to be low. And we can see here there's one, thing that's glaring out like a sore thumb, right? And I put it up here, right? So this is basically saying, okay, we're trying to predict right here, right? This is the prediction time horizon, right? These 2 weeks right here. We can see here that there's a spike in school supplies, right? And I think this was in Ecuador or something, and I'm guessing it's in August, right? That's where we are. We're trying to predict in August. And if you have kids, right, that's when all the school supplies go on sale. That's when everyone buys school supplies, right? And if we look at this error is basically saying, hey, the model was working quite well for every segment except for this one. So how do you deal with that, right? So what I decided to do was a few things. The first is to remove that data set, right? Remove that product segment, the whole thing from my existing data set that I showed you everything on already, right? To say, hey, I want to treat this whole product segment as a different problem all by itself, right? And in this case, I actually felt like I could learn from the historical information, right? And not only that, I knew that based on my knowledge of the world, that there's a school supply sale, or there's a lot of school supplies that are always sold in August, right? So what I did is I say, okay, let's take the average sales in August, and put that as a feature in this new subproblem, right? Or let's create an indicator variable for whether or not this is in August, right? In the prediction time horizon in the future, right? And I created some other features that were like this. What I did then is I fit two sets of models, right? The first is a light GBM for everything but school supplies. The second was another set of models that have all these school supply and specific school supply features with only the school supply data, right? I combine those two models together, right? And using something called like an ensemble, which basically is like you can concatenate your models together and do like a combined inference. And this is something that if you're kind of new to machine learning, it might seem a little advanced, but this is actually shown nowadays to be, one of the best things that you can do for performance, right? And when I did this, I was able to slightly further improve it down to 0.43, which it was around a top 10% in the leaderboard. And mind you, this wasn't like I was spending months on this or anything like this. This was just the logical kind of ordering, and we'd still recommend this. Like if I got a problem I needed to solve today, I would do error analysis. If I needed to improve it, I would do error analysis. I would create some sort of ensembles and custom features for that to try to reduce the error as much as possible. So just to put the pathway on here, and you might be thinking, okay, yeah, we've increased the number of features, and there are problems that go along with increasing the number of features, right? And this is what I wanted to just basically highlight on this slide is, okay, I went from manual baseline, which is the most basic thing, all the way down to using something like residual analysis on ensembling to improve the performance by like 10 to 15%. And in doing so, I kept adding information based on either my automated techniques, manual techniques, domain expertise to increase the total feature set from 30 to 100. Here's also shown that you can see that there was some overfitting that was actually happening here. And you can tell that it's overfitting because the training error was significantly lower than the testing error. But it turns out that when I added in this segmentation approach or this ensembling, it got more close together, which to me is a good sign, meaning that the model is more generalizable. So one major thing that you need to be thinking about in this case is always trying to minimize the likelihood of overfitting. And when you're doing feature engineering, you always kind of have to check, hey, what's the difference between my training and testing error? Are there significant errors in certain segments of the data that are completely overfit, right? And that's kind of how you do it, is this residual analysis. So to summarize everything that I talked about, essentially is, I wanted to give you, if you didn't have any exposure to what the idea of feature engineering is to provide you some basic understanding of that. And hopefully after, the short talk, maybe you kind of get, okay, I have a time series data. These are some of the types of features that I can use, right? Then I wanted to also introduce some sort of, automated workflow. And I didn't want to go too deep into what .data is or anything like that in this talk, of course, because I'm not a sales guy. I just want to get the problem solved as fast as I can. And there's many tools out there that are automated, like including ChatGPT type stuff or TSFresh, as I mentioned. And if you just Google it, there's many, right? But you can never just say, hey, automate this fully, right? You always need to incorporate some sort of domain expertise into the features, right? That's going to be the best lift that you're ever going to get. So I think the combination of automated techniques for simple things like dates and so forth, or just some aggregations, is really important, but never, forget about the domain specific features. The next kind of things I can highly recommend for a workflow is to do feature engineering based on high error samples, right? So if you look through your prediction results and say, okay, are training data is we're not capturing this correctly, right? We don't have enough features to say that school supplies in August are extremely volatile, right? We need to construct some features that be able to do that, right? We need to say, okay, let's add a feature that says it's in August, and that's important. And then your model will learn, hey, if it's in August, the sales are higher, right? And so you need to be able to focus on high error samples and allow you to choose new features you can add to capture those errors. And then, yeah, when I was able to do this iterative feature engineering process, and I feel like this is a really common thing that you can expect. Now, you're never going to minimize the error completely, right? But I would say by doing iterative feature engineering, expecting somewhere in like the 10 to 15% improvement without adding in new data sets. Like I didn't add in like a separate data set that wasn't in that original schema, right? So just by doing some sort of iterative feature engineering and machine learning, I think a 10 to 15% improvement is something that you can really expect to see. And the last thing is, yeah, like I didn't really show it in too much detail, but if you're interested in it, we have many videos, like I said on the introduction, about other problems that we've solved, or our website, of course. But I wanted to just show you a little glimpse of what data is, and yeah, that's basically the talk that I have today. So if there's any questions about what I did or about feature engineering or data, I think I'm happy to answer them now.